In section 2.7, we close out the chapter by looking at square roots and then comparing real numbers, and we're also going to look at irrational numbers, which are part of the set of real numbers. So first of all, square root. If b squared is equal to a, then b is a square root of a. This will make more sense when we see an actual example. If you take 4 and square it, you get 16. That means 4 is a square root of 16. But also notice that if you take negative 4 and square it, negative 4 times negative 4 is a positive 16. So both 4 and negative 4 are square roots of 16. So here you'll see the square root represented like this. We have a radical symbol here, and we're often going to see a plus or minus sign, which means we want the positive root and the negative root of 16. And then whatever is inside that radical symbol is called the radicand, whatever we're finding the square root of. And so here we have, when we're looking for both square roots of 16, we need a plus and a minus for positive and negative. Positive real numbers are going to have two square roots. One will be positive, one will be negative. 0 has exactly one square root, which is itself, 0. And then negative real numbers have no square root. Okay? And then when you see this radical symbol by itself, this is referring to only the positive square root of a positive real number, and that's called the principal square root. So when you see that radical 16 without the plus or minus, that's the principal square root that we're looking for. So if you see something like this, radical and then 36, this is the principal square root of 36, which is positive 6. But bear in mind, 36 itself does have two square roots, positive 6 and negative 6. Okay, a perfect square is the square of an integer. So if you take 1 squared, you get 1. 2 squared will give you 4. 3 squared will give you 9. 4 squared will give you 16, etc. And on it goes into infinity. Okay, we've looked at different types of rational numbers. Now we'll look at irrational numbers. An irrational number cannot be written as the quotient of two integers. In decimal form, the decimal will neither terminate nor repeat. And the square root of a whole number that is not a perfect square turns out to be an irrational number. So if we look at, for example, the square root of 12. 12 is a whole number, but it's not a perfect square. It didn't fall into our list here. It falls between 9 and 16. So it's not a perfect square. And when we take the square root of that, we'll get a decimal that does not terminate and it does not repeat. There is no pattern that will continue over and over again. Therefore, this is an irrational number. So real numbers consist of rational numbers and irrational numbers. And remember that within the rational numbers, we also have the subsets of integers and whole numbers. So that came from an earlier section. Now we're looking at the second part of real numbers, which is irrational numbers. Okay, we can use the idea of perfect squares to approximate a square root. So for a whole number that is not a perfect square, we can compare that number to the square roots of two perfect squares that are close to that number. So for example, this will generally make more sense with an example. 45 is not a perfect square. So look at the two perfect squares that surround that number, and it might help to even make a list. 1, 4, 9, 16, 25, 36, 7 squared is 49, etc., etc. 45 falls between these two values. So we want to look at the square root of 36 and the square root of 49 because those we can find directly. And we can rewrite this because 36 is less than 45, less than 49. In other words, 45 falls between these two values. Then the square root of 45 will fall between these two square roots. And we know those two square roots. There are 6 and 7. So we know the square root of 45 is somewhere between 6 and 7. And then we can look and notice that 45 is closer to 49 than it is to 36. And therefore, the square root of 45 is going to be closer to 7. And so we can approximate that square root of 45 as 7. And if you were to check it on a calculator, it turns out to be 6.7 if you round to the nearest tenth. So let's look at some examples. Evaluate the square root. So in the first case we have a positive whole number and it happens to be a perfect square, which is great. So the principal square root of 25 is 5. In number 2, we need to take the square root first and then apply the negative. So the square root of 36 is 6, but then we take the opposite or negate that to get negative 6. In number 3, we need both the positive and the negative square root of 144. So we're going to have plus or minus 12. And in number 4, we can look at that and you might observe that these are both perfect squares. And so this is going to be 3 over 5. And if you didn't spot that, another trick you can do, the square root of 9 over 25 is the same as, that's supposed to be a square root symbol, is the same as the square root of 9 over the square root of 25. In other words, you can break down that radical into two separate parts, numerator and denominator, and get the same result, 3/5. Number 5 and 6, approximate the square root to the nearest integer. So if we go back to our list, we had 1, 4, 9, 16, 25, 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and 10 squared is 100, and that will get us as far as we need right now. 32 falls between 25 and 36. So we can say that the square root of 25 is less than the square root of 32, less than the square root of 36. So 5 is less than the square root of 32, less than 6. 32 is closer to 36 than it is to 25, and so we'll approximate that square root as 6. In the case of a negative here, negative the square root of 87. Remember that we're going to be negating this so that the numbers that look larger here in our list are actually going to end up being lesser in value because they're negated. So we have negative the square root of 100 less than negative the square root of 87, which is less than negative the square root of 81. So then we have negative 10 less than negative the square root of 87 less than negative 9. And 87 is closer to 81 than it is to 100, so negative the square root of 87 will be closer to negative 9. Okay, tell whether each number is a real number, a rational number, an irrational number, an integer, or a whole number, then list the numbers from least to greatest. So we have negative 5.2. There's a terminating decimal, which means it is rational. You could also write that, if you wanted, as negative 52 over 10. So you have a quotient or a fraction with two integers, gives you a rational number. The square root of 36, well, that's equal to 6, which means that this is, first of all, a whole number, and then that means it automatically qualifies as an integer and as a rational number. Okay, 5.3, that's very similar to that negative 5.2. It just happens to be positive, but it's a terminating decimal. We could write it as 53 over 10 if we wanted. It is rational. And then negative the square root of 40. 40 itself is a whole number, but it's not a perfect square. And so when we take the square root of a whole number that's not a perfect square, we get an irrational. So if you were to calculate that square root, it will give you a decimal that never terminates and never repeats. Now to order these from least to greatest, look at our negatives first. And if we look at negative the square root of 40, that falls between negative the square root of 49, negative the square root of 40, and negative square root of 36. Okay, so negative 7 is less than negative square root of 40, which is less than negative 6. So it's somewhere between negative 6 and negative 7, a little bit closer to negative 6, but definitely less than negative 6. Compare that to our other negative, negative 5.2. That means this is going to have the lowest value. So we have negative the square root of 40, and then negative 5.2. Then look at our positive values. We have 5.3 and the square root of 36, which is 6. So 5.3 goes next, and then the square root of 36. Number 8, rewrite the conditional statement in if-then form. So this statement doesn't have that if-then form that we're accustomed to, but it is still a conditional statement. So rewrite it and then tell whether the statement is true or false. If it is false, give a counterexample. So all real numbers are rational numbers. And another way to say that is if a number is real, then it is rational. Okay, so if it's real, then according to this statement, automatically it qualifies as rational. So another way of saying that all real numbers are rational numbers. Now, is it true? Well, we just looked above at a number right here that's irrational, and yet it is a real number. So this is false, and a counterexample could be, well, the square root of any whole number, for example, that is not a perfect square. So how about the square root of 11? That would be an example of a number that is real, but it is not rational. And finally, number 9, evaluate the expression negative 2 times the square root of x minus 5 when x is equal to 64. So first of all, we'll substitute in the 64 in place of x. So we have negative 2 times the square root of 64 minus 5. Okay, and you can think of this square root as acting like an exponent. So we have to apply that first before we can apply our multiplication or our subtraction. And by the way, oftentimes you won't even see that dot in front of a radical. You'll just see negative 2 radical 64. So apply the exponent first. In other words, find the square root. We have negative 2 then times 8 and then minus 5. Then we have multiplication comes before subtraction. So we have negative 16 minus 5. And finally we apply our subtraction last, and we end up with negative 21. So there you go. That again is the last section of chapter 2. So good luck as you wrap it up and prepare to review for your test. Enjoy.